the idea is you choose a program, a whiteboard program, and then you share this this window on Zoom.
Should I begin? Yes. Yeah. Okay. Yeah. Okay. Just let me zoom a little bit. It's okay. Okay. Maybe it's here. Okay. Yeah. Today we're going to be talking about Earl-Hill's theorem. Which says that for almost all surfaces, the path component, of the identity of the diffeomorphism group is contractible. So let's state the theorem formally. If so we need compactness, we need S to be orientable, and with genus more than one.
Are there any market points or boundary components?
It can have or not. I mean, there's no restriction. We can have boundary or with or without boundary.
With without boundary, and with or without market points.
No, we don't.
So, there aren't any market points, but there could be a boundary.
Yeah. Then.
So it sounds like you're attacking the board pretty hard.
Okay.
But I think actually it's not like a chalkboard. You should be able to write on it pretty gently and it should still work.
Okay, yeah, you're right, sorry. Okay, so with these conditions, we have this then. So if this is compact or orientable, genus with a boundary, then I put 0 here. And 0 here means the component of the identity. It's just that's the argument. So well, as it is a topological group, I mean it means that because every path components are homeomorphic, so it means that every components are homeomorphic. So that's the argument, and today we're going to prove this. And to prove this, I found 2 proofs. The first one, the original one by Earl and Hills, which is rather long, and it uses a lot of machineries like PDE or complex analysis and other things. But another one I found just recently in Hatcher's note, which is very short and it's way better. So I'm gonna use Hatcher's one, and maybe if we have time, I can mention the idea of the other one. So go.
Okay. Yeah. Well, instead of having genus greater than 1, it's probably better to say that the Euler characteristic of the surface is less than 0, because if the genus is 0 and there are 3 or more boundary components, and the same applies.
Okay. Yeah. I mean, yeah, but yeah. So
actually, what we need is the Euler characteristic to be less than 0.
And I mean, to prove this, we will use 3 steps. Let me just mention the steps, and then we're going to be proving the steps. The first one that we first show that we can always assume that S has a boundary component. So the first step, that we can always assume that S, the boundary of S is non-empty. This is the first step we will use. The second one, we show that if we cut S along a path, let me say it like this. S minus the path, I'm going to show P. The path, this is a path. 2 points. In the boundary of S. If we cut the path from S, then the result, it doesn't change anything. It doesn't change the well.
Okay. So S minus minus the path between any 2 points
there must be more restriction, but I will explain that I'm proving this. But just to get the idea, not any path, but some path that more precisely, the path doesn't make S disconnected.
Okay, so this is to eliminate to make boundary have one component less.
This one, if we do this, then the third part is that by doing this we can reduce the case of S to this. Then we only need to prove for this. Why? Because the reason is like this, that I assume that the genus is more than the order characteristic is negative, but I'm going to draw a picture because otherwise it's going to be messy. That's why the second step tells us that we can only assume that it is this, because if you have it can have more holes, but just let's have some boundary components on it. Just let's think that this part, the red part, is the boundary component. And if we cut along this P, then the result would be, if we cut, the result would be, by sequence of cuts. First we cut. Let me just do this carefully. Okay, we have this, and we can add. Let me fix the coloring. This is.
Okay. What are we doing at the moment?
I want to show that why, if we assume that we can cut some path, then it's only sufficient to prove for the disk. Because if we cut this along this path, then the result will be this, and if we cut one more time, then we get the disk.
So this was an explanation of how to reduce the problem to the case of
the disk. Is there any question? Do you want me to explain one more time?
Well, let's.
Sorry, Ed. I don't understand if this was meant to explain why the reduction works or just what kind of cuts are allowed.
No. I mean, I wanted to no, the cuts that we're allowed to make are the cuts which doesn't make S disconnected. I mean, that's the restriction, and I mean, every path with this condition is acceptable. And the thing I just said is the explanation why, if we're allowed to do this, then we only need to prove this for the disk, because we can obtain.
Okay, but you haven't yet explained why we're allowed to do this.
No, I haven't. I was just saying that
Okay.
The 3 steps of the proof.
Okay.
Yeah, I mean, in the end, we only need to prove this for the disk if we do this. And the good news is for the disk is kind of easy and it's well known. And I'm gonna mention, I mean, it's not very trivial, but it's easier than the other.
Isn't the case for a disk some kind of theorem in? I tried to look this up once. I mean, the standard reference is some paper in German from the 1930s.
For this, yeah, I mean, it
was okay.
Yeah, it was in the work of Surf, I guess. I mean, it's an easy application of the color neighborhood theorem. I'm gonna mention this, but it's I mean, Surf did something more general, but yeah, in 90s. So this is the idea. So there is no question here. If there is no, let's prove the first part. So yeah, the first part is that, as I said, I mean, the first part we show that first we can assume that S indeed has a boundary component, at least one boundary component. So let's do this. Just suppose, let's assume the boundary of S is, okay, if that's the case, so look at this vibration, and I'm gonna try and use this vibration.
I think you
okay, sorry.
Probably want to assume that the boundary
yes. Consider this vibration over S. I'm going to explain what these terms are. I should have said that this. So what does it do? It sends F to just F. So this part, the fiber is all the diffeomorphisms of S fixing X. Okay, so if we consider this, what can we say about it? So by the exact sequence of homotopy groups, but by our conditions on S, we know that pi I of S for I more than 1, 2, 3, and more, they are trivial. So we can by exact sequences, we have this set for every we have this, right? It's just, I mean, yeah, there's nothing to explain. And for the case when I is equal to 1, I claim that we have the same thing, not only for I more than 1, we have the same thing for I is equal to 1. And the reason is this, just let's write the terms of the sequence. How can I go to the next page? Okay, yeah. So for I is 1, just look at the terms of the sequence. and we have so to prove that this map, to prove that this map is injective, I mean, one way is to show that this boundary map is injective.
The map in the red circle is injective.
Sorry, isomorphism. To show that this is the red map is an isomorphism, is only.
This map is automatically injective.
Yeah, it is injective. Yeah.
We want to show that
it's surjective. Yeah, to show that it's surjective, it's only sufficient to show that this boundary map is injective. And I mean, and again, this is easy because if we look at the construction of the boundary map. Let me first write, and if you want, I can explain why. I mean, it backs to the construction of the boundary map of the exact sequence. I guess let me write the continuation of this. Yeah. So what does it do? I claim that, and I claim boundary of some gamma is a class of let me show my F. And what is F? F. Let me draw a picture and this is S and this is maybe we have some, and this is gamma. And F is a map. I mean, F is such a map that just for a moment consider the isotopy of the maps between the identity map and the map takes. I mean the family of maps moving x naught from this. I mean along this path. And extend this map to the whole surface. Extend this family to the surface.
Basically, what you're saying is that if gamma has no self-intersections, then delta of gamma is the Dane twist along gamma.
Yeah, exactly.
What if gamma is allowed to intersect itself?
I mean, we can just, it's homotopy to a map, which is so we can choose a representation of gamma which doesn't have a self-intersection.
Well, this is possible for some gamma, but not for all.
Not for why?
Exercise actually, exercise for everyone. There are paths which do not have. There are free loops which do not have representatives without self-intersections. Okay, but on the other hand, if we're allowed to basically, let's assume that we know that the mapping class group is generated by the Dane twist along a family of curves, all of which have no self-intersections. This is in fact true. Obviously, it needs to be proved, but let's assume. Then basically we have all those elements in the image, and so the images everything. The whole panel. But nevertheless, let's try to understand why delta of gamma is F.
Okay. To explain this, it's just by construction of this. How do we construct the delta? It's because it's a general fact. Let me just explain maybe here. For any vibration F, E. So E. We know this that for every I pi I of B and some is just the same as pi I of E and the fiber over X. Right? And we can just say this one is F. So it means that this thing is all maps from the, let me just write this. This is all maps from this. Okay, I use I, so di. Such that the boundary of di goes to X. So, I mean, so the boundary of this is just S minus 1. So we get a map. So this thing, it gives us a map, just the restriction of the boundary. It is in pi minus 1. So this is how we construct the boundary map, right? I mean, by this. So, okay, so look at this again. Is it clear now? Because I mean, look at the fibration here. Everything here is a map. I mean, okay, so every loop here goes to some path, some diffeomorphism of it. I mean, okay, no. Let me say this by this identification here, like this. Okay, this is what? This is a pi one. These are loops on the diffeomorphisms of S, which the beginning and the end are the diffeomorphisms fixing X time. And so I mean, and exactly it is this one that in the beginning, I mean, one of the endpoints is just the identity one fixing everything, and the other endpoint is the one which travels along this loop, and extending this.
Well, actually, the delta of gamma is not the Dane choice. It's no, I don't think it is. Let's consider the neighborhood of gamma. And here we have X node. And then the map does the following thing. Well, it's identity of the boundary and then we transform we transform this this interval, which I've just shown, to how to undo.
You should hold your hand.
Okay, so I'll try to the result. So we so we have something which resembles the Dane twist, but it's
yeah. Thank you. Yes. I mean, yeah. You made something very easy in the future. I have problems with this, but this. So yeah, this is what the map does. It's even bigger for it. So we had a short.
Yes, but then we need to prove somehow that maps of this type indeed generate the pi mode of diff xx mode. So how does one prove this? Okay, let's assume.
Yeah, for a moment. And in Hatchers, there was no mentioning of considering the. I mean, we assume that every map here can. Okay, so our goal is to, this map is injected, but now it's easy to do. Why? Because just doesn't have this shortcut now.
Which one is injected?
The boundary map, the delta. I mean,
the delta map is this delta.
This delta, yeah.
So we hold on. We've just sort of proved that this delta is surjective.
We didn't prove why.
Well, because we calculated the image of gamma, assuming gamma has no self-intersections, and then we assume that pi naught is generated by pi naught of diff. The mapping cluster is generated by elements of this type. So delta is surjective. It's probably not injective.
It must be injective. I mean, how can you say that? Okay, I mean, it can make another generator with only, with this. Yeah.
Well, if delta were injective, then
delta. I mean, I'm going to prove this.
Hold on.
Is this what Hatcher says? I would have first guessed that I wanted to consider the kind of kernel, so to speak, of the map from diffeomorphisms that fix the point to diffeomorphisms and try to identify that with the image of delta. Identify that with that is the image of delta, and I would try to identify it with the loops.
Hatcher said this. I mean,
okay.
Is
it in the same set of notes as the Madsen-Weiss theorem, or is it somewhere else?
No. I mean, they did something completely different.
It's in a different paper.
Yeah, I mean, this one. I mean, this one is in what is in Hatcher's, but I mean, the original proof is very different from this. The method they used.
No, I'm asking, where did Hatcher write this proof?
It's in Hatcher's proof, Hatcher's paper.
Which paper?
In the main one. I mean, let me say
Chris, to answer your question, yes, it's the same thing.
Okay.
Okay. So we want to prove that delta is injective. It's probably not true that it is surjective, because otherwise we would have an isomorphism between pi1 and the mapping class group, which is probably false. Okay, so it's probably not the case that the mapping class group is generated by elements of this type.
But then we have that problem.
Okay. So how to prove that the map is injective?
Okay, yeah. To see that the map is injective, we can just use this. Consider this diagram that. Let me consider this map that pi1. That's not this composition. I'll go by the boundary map to pi. And then we go to the group of and how it sends to some f as we define. And what does it do? It just takes the f star. It sends to a map taking and so this map, this composition is injective because this group, this one, it has 0 center, the center is 0, and so this is the whole composition. Is
hold on. So gamma goes to f, and the f goes to pi mod of diff goes to.
Maybe it was better to write the image of this. Because I'm not defining on all the maps. I'm defining this on the image of this.
So every element in the image of delta acts on the group. Is it by 1?
This is pi 1.
Okay. So 1 s x mod. Well, every element of diff x mod acts on by 1 s x mod. No surprises there. So your claim is that the map, the f, which corresponds to gamma, is in fact goes in fact to the conjugation by gamma.
The reason for this is just use it here closed and
okay. Chris, look at this picture. Does this look like conjugation by gamma on the level of pi mod?
I don't know. This is what Hatcher claims. So his description of what this diffeomorphism should be.
No. This is what Gorinov claims. So you need to pay attention.
Well, what do you claim?
My claim is if gamma has no self-intersections, then the delta of gamma. Sorry.
I don't think self-intersections has anything to do with it.
Well, it's,
so I'm saying Hatcher tells you what the diffeomorphism should be for any loop.
Does he?
Yeah, he didn't say anything like this.
Okay. Anyway, it's hard to draw when there are self-intersections. Let's assume that there are for a minute. We want to understand what this map does to pi1, and the The claim is the resulting map of by 1 S X naught is conjugation by gamma. Chris, do you agree?
I don't know because I don't understand the construction.
Okay, the construction takes the red interval to the red interval. Does it make any sense?
No.
Okay, so we.
I don't understand this picture.
Okay.
It doesn't.
Let's start. Let's start at the outer part of the boundary. As we approach,
I do not understand at all what this picture means with the red in it. It means nothing to me.
Well, I'm explaining.
On the left, I see a genus 1 surface with a loop on it. On the right, I have no idea what I'm seeing.
Yes, I'm talking about the one on the right. The map goes from the tubular neighborhood to the tubular neighborhood. It's identity on the boundary. So let's see what happens near gamma. We have the tubular neighborhood. Let's assume it's a cylinder.
Okay.
Let's start with the outer part of the cylinder. And let's take the outer circle. On the outer circle is the identity. The map is the identity. Then, as we approach X naught, we do the rotation about an angle which approaches 2 pi as we approach X naught. Does this make any sense? Basically, from the outer boundary to X naught, we do the Dane twist, and then we do the inverse Dane twist.
If you say so.
Well, do you understand what I think the map does?
No. I mean, if I just interpret literally what you say, why don't I get the identity? I first do the Dane twist, then I do the inverse Dane twist.
Well, because of the X naught, we need X naught to go to itself.
Okay.
The map is so what we get is a map which is the identity in the mapping class group of the cylinder, but it's not the identity in the mapping class group of the cylinder, comma X naught. Okay, let's try to green circle. Let's take let's draw another circle, green one. Let's draw the image of the green circle. So the image of the green circle will still be the green circle, but this point will go to the circle the lines should not intersect, but it's really hard to draw. Okay, so this point on the green circle moves by some angle, let's say counterclockwise. As the green circle approaches the circle that passes through S naught, we get a Dane twist. So we come back to X naught. X naught must go to itself. Does this make any sense?
No. I don't understand what Hatcher writes, and I don't know what you're talking about. I don't see how this is going to define something.
Okay, let's erase this. Let's erase this picture.
So what Hatcher says is drag the base point along gamma and extend this to an isotopy of S to F.
Well,
I can't even parse this sentence.
Well, it's basically the same thing.
Extend this to an isotopy of S ending at F.
What is F?
Good question. Okay, so
okay.
So
F is the map.
okay, okay, so it's going to be the isotopy class of. I see. So F is going to be isotopy class of the diffeomorphism obtained by dragging the base point around gamma and extending this to an isotopy of S ending at F. What is F? It sounds self-referential, what he writes. He's trying to define F by using F.
It always works, doesn't it? Okay, let's forget the sentence. Let's look at this picture again. Okay, in this picture we have in the top cylinder we have the green thing and the red thing. Let's see where the intersection goes.
Let's go back further. Here, this sounds like it's just some ansatz. It's a guess as to how can I build a diffeomorphism starting with a loop. But this is not what we should be doing. We should be considering this vibration and figuring out what is the correct connecting map. Yes? So we need to take a loop in the surface and we need to lift it to a path of diffeomorphisms.
On the path, we want to have an element of pi naught of diff.
Yeah, but what is it going to be? I mean, Salman said, you're going to lift it to a path whose two endpoints live in the fiber.
I mean, just the construction of the boundary map, like the way we construct, so we can just think as every path in.
So here, n equals 1, so it's a path.
I mean, for I is equal to 1, I mean, every path, every loop here is a path, which the endpoints are in fixed diffeomorphisms. So, I mean, for the thing I got from Hatcher's note is that, I mean, by this loop here, I mean, here at 0, I mean, we have identity, the isotopy, and at the time t, I mean, we move here as time t. So at 1, we go with this loop 1 time, and we just extend this for every time t. So it gives us an isotopy of the surface, and so this is our f. So f is at time.
One more explanation. Suppose we have a cylinder. So we have what's a cylinder? A cylinder is S1 cross 0, 1. Okay, so we have pi naught of the cylinder, and we have pi naught of the cylinder, comma x naught, and there is pi naught diff. There is a map from the second pi naught to the first pi naught, just by forgetting the point. My claim is that the kernel is dead. Chris, do you agree?
This is pi naught of diff of the cylinder?
Pi naught of the diff of the cylinder, comma, x naught, goes to pi naught of the cylinder without x naught, forgetting about x naught.
So what is the kernel?
My claim is the kernel is Z.
No. What is the generator?
Well, try to imagine the generator and you'll understand this picture.
Well, it's supposed to be the same thing that Hatcher says, which is just drag the base point around the loop.
Exactly, and it's the same thing I've tried to draw but failed.
Okay, so let's suppose this makes sense. So there's a diffeomorphism, there's a path of diffeomorphisms, which is like, you know, draw a little open disk around X and start dragging this around.
First in one direction and then in the opposite direction.
I don't understand that. Opposite, first in one direction, then the opposite direction. What if I just go all the way around once? I come back to where I started. The base point comes back to where it started.
Sorry, I didn't catch that.
If I just go around once.
Yes, if you go around once, you get the Dane-Weiss. The Dane-Weiss does not preserve.
So, I don't know. I don't understand. So I just drag the base point a full loop around the loop, and the
Yes.
base point comes back to itself.
Yes, this is it. This is it exactly. And then you extend this to the Hell cylinder. Exactly.
That's fine. Okay, fine. And then we want to see how this acts on other loops with the same base point.
We want to see, and Hatcher claims its conjugation.
That it's conjugation.
By gamma or gamma minus 1.
So, and so this composition, I mean, as the center of pi1 is 0 for most of the surfaces, so we have this objective. So I mean, so
okay. So we want to assume that the center of pi1 of S is 0 if the Euler characteristic is less than 0.
Is it comes from the classification of surfaces?
Well, yes. If there is boundary, then the surface is pi1 is free of rank greater than 1, which means the center is definitely 0. And if the surface is if there is no boundary, well, let's assume that we know that the center is also true.
I mean, yeah, it comes. I mean, if you want, I can. I guess it's clear from the.
Well, it's easier than.
Yeah. Okay. So by now we proved this. Let me just recuperate here. And so for now we proved this. Sorry to line, but we proved this that for every I. It looks like J, but it's I. We have this pi this. It's just the same as isomorphic to pi of this. And we needed to. Oh, sorry.
That's Okay, so we sort of proved that the higher homotopy groups are the same in both cases.
Yeah. So now we use this to prove that we can always assume that S has a boundary.
Yes. So now we want to understand the relation between S, x naught, and S mod the boundary.
So now look at this vibration again. Okay, no, before I say this, just around, fixed. It's because we want to create a boundary. So to create a boundary, we need to remove a disk. So choose your favorite disk. Fix a disk around X naught. Call it. So we have this vibration that we embed. The fibers are the diffeomorphism fixing the, D and this, the fiber is this. Just this. The notation is clear, right? The diffeomorphisms of S fixing D and S. Okay. It's, we don't need them because if it fixes D, it fixes this. It's not too so.
Okay. Now, we want to prove again that the homotopy groups, the higher homotopy groups are the same.
Yeah. And again, okay. So for this, first of all, this is a general fact from any dimension. Let me state it as a lemma or something. For any dimension, this space, the embedding of any dimension of this to any n dimension. It's just homotopy belong to G and R. And the map is easy. The map is just case. Okay, so sorry, I should have fixed some base one.
So basically, you want to yes, you want to include the base one as well.
Just by taking derivatives. So it tells us that this one is, it's just homotopy belongs to S1 because it's GL2R.
Okay. Chris, do you agree with what it says on the board?
I think so, yes.
Okay, Grisha, do you agree with what it says on the board?
Yes, I think so.
Okay, so let's assume this then.
Okay, so if you assume this again, we have, if we look at the exact sequences, we have this. We have two cases. The first case is for, again, I greater than 1. We have, where was it? I of if S, let me remove this part. It's the same as I of if S is that. And so we need to consider for I is equal to 1, and if I is 1. Again, if we write down the exact sequence, zero of again, I need to show that. To show that this red red. If I want to show that this red one is isomorphism, I need to show that the boundary map is injected. But here we have an easier case because what is the generator of this? The generator of this, it's by just rotating the disk by itself, in any direction. And if this goes here, it's just the extension of the dentures around that boundary.
Okay. So the boundary, the generator of that goes where? It goes to
dentures around or around? Which is
to the dentures about the boundary of S. Sorry, the boundary of D.
The extension. I'm sorry, the extension.
So basically, we take S and we take D. We do the 2 pi rotation about the center of D, and we extend this to an isomorphism to self-diffeomorphism of S. Chris, does this make sense?
So I'm always a little confused by these things. Does it mean, okay, I have the, standard embedding, like we fix coordinates, I have the standard embedding of a disk. And then I could first just spin the disk a full turn.
Yes.
And then if I do that, every point on the disk comes back exactly to itself. It's just the identity automorphism of the disk.
That's the diffeomorphism.
But it's the identity on the disk itself.
Yes.
And then I embed. How is that different? How is so you're saying as a path in the space of embeddings, this is a non-trivial loop. So I could when I'm embedding it, I can first turn it by an angle theta and then embed it. And so there's a theta family of embeddings. And the claim is that this loop of embeddings, although I come back to where I started, is not contractible.
Yes.
And the reason it's not contractible is I do this I do this construction in the lemma. I take the differential, I take the derivative along this family, and I should get a non-trivial loop in GL2.
Exactly.
Okay. So this is the claim, and the claim makes sense. I can parse it. I can try to do the calculation myself. I'm always a little confused why this works. Okay.
Okay. Now so the question is why the result is non-trivial in pi naught of div D, and it's more or less clear. But still, if there is a proof, let's see.
Well, it's all. I think we just said what calculation you have to do. So you write down this theta family of embeddings, and you compute its derivative, and you get a family of matrices in GL2, depending on theta, and you just inside GL2 you know how to tell whether or not a loop is contractible.
Yes. Basically, it's not GL2. It's better. It's even S02.
Here it's
okay. Now yes. So we may assume that all those matrices are orthogonal, in which case
Well, is it SO2 or O2? Because we're looking at just embeddings, not oriented embeddings.
In general, it's O2, but in our case, when we take, in our case, we take a map from pi1, which means we take a path.
We fix a base point.
Which is in the same component as the base. In our case, it's SO2.
No, but in the statement of the lemma. Also, our diffeomorphism groups, are they just diffeomorphism groups or oriented diffeomorphism groups?
Well, so far, I think it's just diffeomorphisms, but where we want the path, we want the components of the identity, in which case we can take one or the other. It doesn't matter.
Okay.
Okay. So blah 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 blah. Well, let's erase the.
So anyway, we conclude that because the Dane twist is non-trivial, this map is injective. Oh, the Dane twist is non-trivial and of infinite order, and therefore this map is injective.
Yes, but let's. Is there a simple proof that
for this? Yeah, I mean,
well,
yeah.
Let's see.
I mean, this is very short. Again, we can factorize this map by. I mean, we want to show that this map is injective again by the same trick. I mean, map is to class. And again, back to the other part of yeah, to this one, map to here.
But I mean, automorphisms.
Oh, sorry, pi1 maybe. By doing this, I mean, again, this goes to a Dane twist. Just, let me show the Dane twist by delta. And again, what this does, by doing this method.
So now the claim is the generator 1 on the left goes to conjugation by delta, where delta is the boundary component, and the boundary component is non-trivial in pi1.
Yeah.
It could be trivial in homology, for example, but not in pi1. And the claim is that this conjugation is in fact a map of infinite order, which means delta is injected.
Yeah, that's because.
I mean, I thought in fact that the Dane twist should even be of infinite order in homology.
Well, it depends on homology of what. Now, here we're doing the Dane twist along the boundary circle. In homology of the boundary circle, if there is, imagine there's just one boundary component. Then the boundary of the boundary circle is the boundary of everything. The boundary of the fundamental cycle. So in homology, it's 0. But in pi1, it's not, and let's assume that if we have if we have at least one boundary component, then conjugation by this element is not trivial, and let's even assume that it's
because here
in order. Well, there is another way to prove the same thing. Namely, in mapping class groups, there's a standard technique called systems of curves. Okay, let's forget about systems of curves. Well, here is a straightforward proof. Risha, does this argument make any sense whatsoever?
I'm happy.
Risha.
Yeah, me too. Yeah, it's fine.
Okay, so
My only question is, so on the right-hand side, do we really want pi1 of s minus d, or just pi1 of s at the marked point? Because
we want pi1 s minus d.
Because otherwise,
so where's the base point for pi1 then?
sorry, the base point, I forgot to, I mean, take a base point and the boundary of the, just base point of y naught, where y naught is here. I mean, take a base point here.
Yes. Well, let's take the base point at any point of the boundary.
And we remove the interior of the disk then.
Yes.
So okay, so if it is okay, so we so far showed that for so combining all of this together, we show that for any I and diff 0. I mean the
Okay. So we proved this for the whole diffeomorphism groups of the higher homotopy groups of the space are those of its component that contains the base.
so we can assume.
So as a result, we may assume that S has boundary. Okay.
So a question though about these types of arguments. Is it obvious that the sequences we wrote down are fibrations?
Yes. I didn't check my hands, but
all surfaces we have in this proof are compact. So basically, if you're mapping something compact anywhere, then all those mapping spaces are fibrations in the literal sense.
You're saying,
well, for example, if X is compact, then there's a map from maps X, comma X naught. Okay. Okay, let's forget about diffeomorphisms. Let's look at the mapping spaces.
okay.
in particular.
So we have the evaluation map from
Yes,
this cross X to Y, and you're saying if X is compact, and I evaluated a particular point, that this will be a fibration.
Yes. Okay. Why is this so?
Yeah, that's fine.
Okay, so if all spaces are compact Hausdorff, then we have the exponential formula, which is true on the level of spaces. If something, okay, if some of the spaces aren't compact, then there is a way to get around it. Let's not worry about this because all our spaces are compact. So the let me try. Okay, I think there is enough space here. So we have in particular we have. We have the sequence we are interested in. If X is a compact Hausdorff, then the sequence is a genuine fiber bundle. And the same. The same happens in the smooth category, and there's just one reasonable topology for spaces of smooth maps if the source is compact. And if the source isn't compact, then there are several, and so on. Chris, does this explanation explain anything at all?
I mean, you asserted some well-known facts, and then the last thing is the thing that's actually interesting. What does it have to do with this exponential formula?
Nothing. It's just, or maybe it does, but it's just two separate facts.
Okay, so
separate facts which are true for compact spaces.
So I don't expect a proof, but I mean, what does one have to observe to check that what you wrote down is a fibration?
I don't know.
Okay, but anyway, this is some well-known fact, and I should go educate myself.
It is a well-known fact. I just don't remember how to prove it.
Okay, that's fine.
Okay, so we need to have a break at some point.
I mean, 5 minutes. Let me just do.
Okay, so let's come to logical to logical point we'll have a break, and then we'll have a break.
Yeah, I mean, just in 5 minutes. I mean, just there is only one thing which I just state, and the proof would be after the break. So, I mean, so we proved that we can assume that it has a boundary. So let me just provide the materials for proving that we can remove the path from this, and then we'll have a break. So just now the second step is that the boundary of S is not empty yet. And consider smooth path, yeah. Alpha. Smooth. That I mean, Q and both, yeah. In one component, no. Sorry, just they're in boundary, maybe not necessarily in only one component.
It's P and Q are both inside both elements of the boundary, may or may not be.
Yeah. I mean, it can be different.
The same boundary.
Yeah, and this space, assume this space that A S alpha, just these are paths starting and ending at P and Q, isotopic to alpha. This space, so all paths starting at P ending at Q that are isotopic to alpha. And just for, I mean, I'm going to prove this after the break, but I mean, the claim is that this space is contractible, which is very not very, but I mean, is not trivial. And
so AS, alpha is the space of paths which start at P and at Q and are isotopic to alpha. Okay, so again, isotopic or homotopic?
Isotopic.
Okay, what if alpha, is alpha allowed to have self-intersections?
So maybe we can, I don't remember, maybe we can consider it as homotopic. But let's just have homotopic in future reality problems we get. So for a moment, let's just assume there.
Okay, so yes, so
and by this,
okay, so we want to consider the space of all paths which are on top.
Yeah, and by assuming this, then we'll have a break. I mean, after looking, by looking at this vibration. Again, sorry, I have to see here. So this vibration gives us that these two spaces are homotopic.
Okay. So what is the first space? If this has
diffeomorphism of S fixing alpha.
Does this mean diffeomorphisms which preserve all elements of
no, just alpha. I mean, just the path, because alpha was a path here. I mean, just this. Really fix it.
Okay, so what does it mean that a diffeomorphism preserves preserves alpha?
Okay.
Does this mean that F preserves all elements in the image of alpha?
Yeah. Yeah. So I mean, so this tells us that, I mean, by accepting this fact, which I'm going to prove after the break, that this space, where was it? This space, by assuming this fact, So this tells us that diffeomorphisms of S are
hold on. Why does F alpha? Why is F alpha
is
homotopy to alpha?
because I mean it's in the path component of
because F is in the component diff node.
Yeah, if F was not in this component, it wasn't homotopy to alpha.
Yes. Okay.
This one is nothing but diff S minus alpha. So so this reduces the case to the disk, and for the disk we know that it is contracted. So after the break, I'm going to prove.
Hold on. S minus alpha of I.
I mean, I should have added again.
S minus alpha of I is
The image of
is non-compact.
I mean, but by cutting a line, but I mean, then take closure. I mean, just cut a line. I mean, how to write this form. I mean, just cutting a line alpha.
Okay, so the claim is again, we need to assume that alpha is does not have self-intersections.
Deep closure.
So if alpha has no self-intersections, the claim is diff node as alpha is the same as diff node of S cut along alpha. Chris, does this make any sense?
Yes.
Chris, what do you think?
Why isn't that clear? Because I mean, just fixing here, because it's facing around. These are the ones who are faced there.
Okay, so let's assume alpha has no self-intersections. Then diff S alpha, meaning the space of all diffeomorphisms which fix alpha pointwise, is the same as diff S cut along alpha.
Except,
we
yeah,
more boundary components, but all our diffeomorphisms are assumed to be identity on the boundary, so it makes sense. What do you think, Chris?
so I don't know what we mean really by cut along alpha. So it probably means take an open tubular neighborhood around alpha and delete that.
I mean, just delete alpha and then take closure.
But no, that can't be right? Because then take the closure where? Inside of S? Won't that give back all of S?
If you can embed your
I think you must have to delete an open tubular neighborhood. And then that leaves some new boundary components.
Yeah, okay, so let me just
But then don't we want maybe the diffeomorphism to be the identity in a neighborhood of alpha? Is it really enough that it's just along the points of alpha?
Suppose we have some manifold M and a submanifold N of codimension 1.
Mm-hmm.
Then there's a unique M bar. There's such that. the complements are diffeomorphic and
And I get this by taking the tubular neighborhood of alpha and deleting it, or the tubular neighborhood of n and deleting it.
yes, but there's a way to construct a closure of m minus n.
You're saying there's a kind of
there's
canonical way to do it without choosing a tubular neighborhood.
more factorial way to cut m along n. Let's see if I can remember. Let's see if I can remember.
Mm-hmm. Let's see. It maybe involves something like
I can't remember it. Maybe
I think I've seen construction. So if I remember, it might involve something like taking a limit over all choices of tubular neighborhood.
well, let's think about it during the break.
Okay, that's fine. Let's take a break.
Okay, so basically what we did, assuming this homotopy equivalence, we did reduce the statement that we're after to the case of the two-disk, and basically there's one problem. The two-disk has Euler characteristic greater than 0.
No, I mean, we can prove this separately, just.
Okay, well, let's talk about it after the break.
Yeah.
So break 20 minutes. Okay. Chris, are you here?
Yes, I am.
Grisha, are you here?
Yes, yes, I'm here as well.
Okay, so let's continue.
So okay, we were about to show this. Okay, so let's prove this. Okay, so we prove this. Okay, we want to prove. Let me show one more time. We want to prove this. And to prove this, we consider two different cases. The first case is when alpha connects two different components. Sorry for the yeah. So we first we consider this case, like just components of a boundary force. So let me just draw pictures because I want to explain something more in the picture. So just assume that here is P, here is Q, and alpha is connecting this group. So from this is S. So construct T as follows. Let the icon is T be this. Be this surface. Be this surface that we just add a disk along this button like this. I mean, we added a disk here, so this Q is T. Okay, so let T be this surface. So for this surface, this
Okay, what happened? We filled in one of the boundary components, or both. With
no, one of them by this, and the other one we didn't touch. Okay, so consider this vibration again. The namings I'm gonna explain because I mean I'm gonna write embedding, but they have more restrictions. This is base. This is. This is embedding. Okay, this one, I mean, this one, the base, this is just the embedding. It's there's nothing more restrictions. But for this,
once again, embedding of
not quite a base. I'm gonna explain just now. I mean, this one is the, I mean, the embeddings of, I mean, first connect. How to say? I mean, just glue. One with a, I mean, 2 points in. I mean, just this is, I mean, so I mean, this thing is connected. It's just they're not.
What is T?
This is just okay. D is just a disk.
Okay, T is the surface plus the disk.
T? No,
Yes.
no,
T.
T. T is just the surface that we have as surface.
Okay, so S is the surface.
S is the main surface that we want to prove this.
Given and T is the
yeah, T. I mean,
T is the surface with the disk
with some relations. I mean, some.
Fluid along one of the boundary components.
Yeah. So it's and okay. So first, I mean, by the union of I and D, I mean, first glue one of the endpoints of I to the boundary and 0 in I must map to T, and the rest must go to the interior. So this is the condition on this. I mean, as I said, it's a bad notation. I just named embeddings, but
what about the third space?
it's just embeddings. I mean, this one is only
embeddings of the disk.
Of a disk
of the
and
disk
and
T minus boundary of T. What does it have to do with that?
What? Let me think. I mean, you mean the
the third space, E and B, one on the right, E
yes.
and B of the two disk in T minus delta T. What does this space have to do with that? What's the map from the second T?
I will explain it. I will explain this. I mean, it's just I mean, restriction of this, and you just take F to F restricted to. You just forget about the integral.
Yes, but D2 basically is the disk we added, so it doesn't go to.
No, it's not this disk. No, this D2 here is not this D2. No, it's just different. I mean, it can be everywhere.
All right, can you scroll up a bit, or is this T the first thing that appears?
Cool.
Is there you wrote let T be this? Okay, so what is above this?
Which one?
So we made the cut. We made the cut along the surface S.
No, you didn't. I mean, no. Let me explain one more thing from the beginning. Okay, I have a surface S, and I have a path alpha with this condition that it connects P and Q, and this with the P and Q are in different components.
Okay.
So in this situation, I consider surface T by having the disk at one of the at the component of Q.
Okay.
This is T. And now I want to consider this vibration, the embeddings of any disks in T minus the boundary, and fiber restricting like this, and the fiber is path.
But still, if the image of D2 intersects the disk we added, then the second arrow doesn't make sense, does it?
Yes, I don't know why. Let me.
So you want in the space on the right, you want.
For example, it's something like this. I mean, just.
Okay, so in the space on the right, you consider embeddings into T minus minus. Okay,
it's here. I mean, the boundary. Yes. The boundary is only here. Yeah. Is it here? Okay. And these are just I mean, embedded paths.
So if I were just doing this topologically, and I didn't worry about whether or not it was embedding, then this would just be, I guess, S.
Yeah, I mean,
but
you don't need.
But here they're embeddings, So what is the homotopy type of this thing like?
I mean, that's what I'm going to explain later. I mean,
Okay.
Starting at P, ending at Q. So this is
Okay.
Okay. And here's the thing. This one, this one is contractible. Is it clear or no? Because I mean, it's just the same argument as not the exact same, but I mean for any space, the path of the space of any path has an I mean, it's just the same because I mean you can shrink everything to your initial, right? I mean you can first. I mean okay, look at this way. I mean first forget about this t, forget about this one, and you can just make it shorter to something here, and then go to again.
Well, this shows that this space is connected, but why is it contractible?
Why is it contractible? Because okay.
For example, just half an hour ago, we did consider embeddings from D2 to the surface, and there was a contribution from taking the differential.
Mm-hmm. Yeah. Okay. Yeah. Why is this contractible? Hatcher said it's trivial, and I thought, I mean, yeah, I mean, in my mind, there was that argument that, I mean, it was about connectedness, not contractibility. Let me think.
Okay, for example, the space of embeddings of a point to x is x.
Yeah.
It's not necessarily contractible. Well, here we have embeddings of something which resembles a point. It's not really a point, but it's contractible. The space we embed is contractible. The space of embeddings is not necessary.
So what is the contraction? So given an embedding, like, okay, there's the constant embedding that takes everything to the point Q, for example.
Well,
and then you want to say that everything else kind of
maybe
that the whole space contracts onto that.
No, Chris, there is no constant embedding, but there is a preferred embedding.
Sure, you're correct. Sorry. Of course, there's no constant. Okay, so the preferred embedding is stick the disk onto the end of T where we attach the disk, and let I go to the preferred path alpha.
Yes.
Okay, and now suppose I have some other embedding, and so I want to kind of contract everything else onto this special point. So what is the kind of standard path from a general embedding to this special embedding?
I'm thinking about something. I mean, maybe we can consider them just maps, not necessarily embeddings. So, even so, I mean, then we can just shrink everything.
What do you mean shrink everything?
I mean, just.
Well, I think we made it. We don't want to consider all embeddings. We only want to look at those which such as the restriction to I is homotopic to alpha or something like that.
I mean, we are not fixing it in Q, so I mean, with respect to endpoints, what do you like? Because if you just fixing, I mean, first of all, it must start from P, not here. But if you just fix P, it is totally to alpha verse. That's the only restriction that starts from here.
Okay. Okay. Do you have Hatcher?
Okay, so I see Hatcher here. His argument is not, he doesn't give like a deformation or retraction. He gives a fibration to a contractible space with a contractible fiber. So he says, given the embedding restricted to I. And so this gives a map to the embeddings of I into T.
Okay.
And he says that's obviously, okay, so this is the space of embeddings that takes 0 to P and the rest of I into the interior somewhere.
So P is fixed in this.
Yeah, P is fixed, but the other endpoint of I is free to roam. It's just in the interior. And so the claim is that this space of embeddings is contractible. So that's the contractible base. And the fiber is what? It's embeddings where the embedding on I is fixed. So once we fix that, we have to do something with the disk.
Okay. So EMB is not the space of all embeddings, it's a space of all embeddings such that one of the ends of I goes to our fixed point
here
to the point P.
Yeah, here, I mean, I wrote here, 0 must go to P.
Okay.
Go to there.
Yes. Well, in that case, it's plausible. It's plausible that this space is contractible.
Okay. And then the fiber is what? It's an embedding from I union the disk, which is fixed on I, that data is given, and then the additional freedom is what to do with the disk. And the claim is that additional data is contractible.
Okay.
Which also sounds plausible. I mean, you feel like you can just kind of, you could just shrink the disk down to, well, you can't shrink it quite to a single point, but.
Not to a single point. I mean, the argument I had in my mind was to, I mean, if you just consider any fixed embedding, then you can shrink every other embedding to that thing. So.
Okay. Let's assume that the space in the middle is contractible.
This is
Okay, and so then the homotopy groups just shift dimension.
Yeah, and moreover, I want to show that this space, the right space, this one, I mean, for I bigger than 1, I1, sorry, I, this one, embedding of to T minus the boundary is 0. This is another claim, and together they show that the path components of the left one, the fiber. I mean, they show that, yeah. I mean, if you take the path components of the fiber, it's going to be contractible, and one of the path components is this, right? It's this one.
Okay.
So we need to.
Chris, does this make sense?
Go down. So what is the claim that's supposed to make sense?
The claim, if I show that for I larger than 1, this space, I mean the pi I of this, all of them are 0.
Mm-hmm.
Then I can show, and then we can see that for the fiber of high ones, for I larger than 0 are trivial. So the path components are contractible. And one of the path, I mean,
that's fine.
I mean, the embedding
That's just dimension shifting.
Yeah, I mean this is. So I mean this is. So let's show this one. And again, for this, consider the vibration. What vibration? A lot of vibrations. Yeah, this one. In this one, I guess this is easy to see. It's not hard as the previous one. Just T. These are, and then the fiber consists of embeddings. I mean, let me just. Embeddings. Just, I mean, fixing what, I mean, okay, for this node does this. Just, I mean, take a point in D for any point.
Probably in theory.
Yes, yes. Okay, so and let's see, is it easy to see? Okay, this one for this now here is clear that for pi I is equal to 0 for I larger than 1, and this one okay, this one is clear that it's contractible again, but what the final?
Yes, the surface T has at least one boundary component. Y, by our assumption, alpha connects two boundary components. One of them survives. Okay, so by so T minus delta T is has three fundamental groups.
So and I mean for this, we have this, and this space, the embeddings of D2 in T minus the boundary that fix X naught is contractible.
Y isn't Hamilton equivalent to S1?
It's not S1. Let me see.
Well, again, we can rotate embedding and get another embedding.
Yeah, okay, yeah, I'm sorry. Yes. It's not point. I'm sorry. It is. Again, I mean, it's that general fact that I said that it's GM2. So, right? It's
yes.
Yeah, it is. Or O2.
Or O2.
Yeah, I'm sorry. Yeah, it's not contracted. So, I mean, again, so it has pi I. 0 for I larger. So it proves the claim. So let's back to the up and see what we've done. Okay, so for this, this one pi I. Let me write for this pi I are 0 for I more larger than 1. And if we write down the exact sequence, we can see that this one tells us that pi I are 0 for I larger or equal than 1. Okay. So and then so it tells us that the connected components are contracted. That's one case, and the other case, the remaining case. So is there any question for now? So we can get to the next part. Okay, I guess we are done with the iterations. Yeah. So I mean now it needs a different argument. So the second thing is that how to use it? Yeah, alpha connects P and Q such that Q are in single. Okay, so just as a picture, it is like this. That we have S here, something we don't know what's inside, and it is P here and Q here, and alpha does this. This is S. Okay, again, we construct another surface T, so let T be. T be like this. Attach one handle to S as well. It's like we have S here. In a way, it is a one handle. In a way that our one handle is, its two sides are in different positions of P. It's not like, it shouldn't be here. It should be in left and right of P. Is it clear, the picture, or no?
The small one handle, which is close to P.
Yeah. The point is it shouldn't be this side. One side must be the other side of the P and the other side.
Well,
left and right.
More precisely, we have 2 points P and Q, and the handle should separate P and Q.
Yeah, or in other words, it must. After doing this, we must have P and Q in different boundary components. That's the point of doing this. So okay, so the result of this is that P and Q are different boundary components. Okay. So and let me just on this picture again. Let me consider. The picture is not that big, but consider such a path. Yeah, just beta, and I guess I don't need to formally define this here. But transverse to the which one is the here, I guess, or I don't know. But if you want to be precise, so I guess this one is the belt sphere, right? This one. So choose beta. Joining 2 points of the boundary of the one handle, which is transverse to the belt sphere of our one handle. So the picture is like this. So after doing this, and what was the name? I guess I used U as a name. And then let U be again. How to show this? I want to say that I want to cut from beta, but yeah, I can't get closure the way I had it. But I get just T cut by. So it looks like this. That again, this is S.
so T cut by theta is.
But I mean, it must be confined.
Basically S.
Yeah, it's homomorphic to S. Yeah. It is homomorphic to S. Okay, so these are the notations, and now let's. What I want to do. Let me. Okay. First of all, by saying this, that P and Q are indifferent boundary components, and by what we just proved minutes ago, we have this, that AT alpha is contractile. This is one thing. Because they are different components. And okay, this is one thing. And okay, wait a second. Okay, yes, this is what I want to show. Now we want to show that this map, for every I want to show that the induced map from the inclusion, this. I mean, let me just write for a second. U. Is injected. Right, because this one is 0, the right group is 0, and to show that this one is 0, I need to show it's injected. Okay, so to do this, I want to lift this inclusion to some covering map of T. So consider the covering T prime, the covering of T, covering of T as well. Okay, to be formal, it is this. I mean, I want to consider that this covering, first of all, what is the pi 1 of T? It is by Van theorem, it is pi 1 of S star C. So consider T prime to be T prime covering corresponding to this covering. So we can say agree to that covering. And then as a picture, it's like this. I mean, if you want to draw a picture, it is S Q, and these are our two one angles, and this part is U, and the red parts are UTL, the universal cover of U. Is it clear that this covering, I mean, this is C prime? Is this, I mean, the covering corresponding to this subgroup?
Yes, so the claim is T prime is so to get T prime, we'll take U, and then we attach two copies of the universal cover of U. Does this make sense?
Because I mean, because what is U is some hyperbolic surface.
I I don't understand that. So we want the cover of T.
Yeah.
T is the surface with the extra one handle.
Yeah. I mean,
what's the which one is so T prime is
T prime is the whole thing.
Okay, what's the map from T prime to T?
What's mapped from T prime to T? I mean, it's just, I mean, and here is just the projection of universal cover, and here, I mean, again, is identity and the middle part, because it's part of U. Is that clear?
No, I'm not saying it's wrong, but I don't understand how it works.
I mean, you want the maps to the map to T, right? Okay, so the map to T, I mean, on here and on this part. And this part is just the projection from the universal cover. Here is clear, and the red part.
No. Okay, I don't even understand. I don't even understand why this is a covering map.
Okay.
So the middle part.
The middle part.
The middle part is U.
Yeah.
It maps identically to U. Okay. Now one of the red parts. Let's say the right one. It's the universal cover of U.
Yes.
So basically, this this universal cover of U maps where?
I mean, this part, well, this part would be mapped to the cut handle, and the rest would be mapped to the inside. To S. So I mean, this part would map to S, and this part to the part of the one.
Okay. Well, now I see how you construct the map. Why is the image of phi 1 equal to phi 1 less?
You mean this?
Yes.
You mean why is it true, or why?
Why is it true?
It's because by Van Kampen theorem. I mean, just
why phi 1? Why is phi 1 of T prime equal to phi 1 less?
Okay. Because again, by Van Kampen theorem, because this part, I mean, first of all, consider this covering. So here it has phi 1 0. The red one on the right has phi 1 0, and this one again by induction 3.
Okay, Chris and Bridget, does this make any sense?
I got lost because I'm not sure. I can only see part of the screen at the moment.
Okay, which part?
Maybe show further up.
Let me zoom out. Is it better now?
Maybe. Okay, so what's on the previous page? What? No, that's probably enough. So U is T cut by beta. And what is it that we want to show? We're still trying to show that this alpha, this A space comma alpha thing is contractible, yes?
Yes.
And what do we need to do? What remains to do? Pi naught or pi 1?
I mean, first of all, let me explain one more time that I constructed with yeah, first the case that P and Q are in the same boundary components. Then I constructed T as follows. So in T, P and Q are in different path components. So we know that A T alpha is contractible. So to show that, and then I constructed U as follows. That I constructed U as a surface homomorphic to S, just this way. Do you see the screen, or no? Maybe you don't see the screen.
I see let U equals T cut by beta.
What? Sorry. T cut. Like that. When it's like here.
No, I see this. I'm just telling you what I see.
Okay. Yeah, it was correct. Yeah. So U, this is U, and this is homomorphic to S. So I want to show that this group, that A S alpha is contractible. But as S is homomorphic to U, I need to show that this space is contractible. And to show that this space is contractible, I need to show that for every I, the induced map from the inclusion on high i's are 0, because this group is 0 for every I. Because T has because we proved for T, because P and Q are different path components of T. I want to prove this. And for this, I considered a covering of T as follows: this picture. And that's what we do.
Okay.
Is it clear that what the covering is? Yeah, and then pi1 of this covering is pi1 of this. Yeah.
Even assuming you've constructed some cover, then what?
Yeah. Actually, I don't need this to show, but I just said, I don't know, if this problem is not important. So let me sober was okay. Yes. Now I can lift and path. To T prime. So take a path which is homotopic to alpha and lift it to T prime. And call this space and put everything into a set and call this. So just as a notation, A prime of T alpha is the set of all of these lifts. Okay.
To do this, you first need to choose some lift.
Okay, sorry. Yeah, lift into this. Lift into the middle one, to the U.
There is a preferred way to lift now.
Yeah.
But since this is a covering space, we're able to lift all paths which are homotopic to alpha.
Just as a notation, because it is T prime and it's different from S, let me just call this alpha prime. It is the same because it's just the inclusion there. But so yeah, lift path here, homotopic to alpha, and to do the path homotopic to alpha prime, like this, and call this A prime of T alpha. And so, it's clear that, just because we lift everything, so it is diffeomorphic, it's not that homeomorphic to A prime T alpha is homeomorphic to S alpha, right? Is it clear? Because, the way we lift it.
There's a unique way to lift a path hold on. If we're given a homotopic between alpha and some other path, then there's and if we have a preferred lift of alpha, we can lift the other path. But here we need here we in this construction we use a homotopic. Which is a different homotopic, we might end up with a different path. So why do I have this?
Okay, let me because wait. Because I guess it's because of the construction. Because I mean, when you look at let's look at T. I mean, everything. I mean, it's just the same. How can I say this? If a path goes along this handle, it's definitely not homotopic to alpha, right? And we're not considering this anyway because it's not in U. So everything. I mean, there is one correspondence. Because I mean, we are considering in U every path in U, and we are lifting this up, and we are not considering such paths. So
so once again, we consider paths where in which surface.
Let me, maybe I'm mistaken, but I guess in T, every path in T, homotopic to I mean everything here, every path here, every path here, homotopic to alpha. But it doesn't concern anything like this.
Why not?
Because it's not homotopic to alpha.
Why is it?
Why is it? Because I mean, again, we can just use stuff like Chapman theorem to say that paths here are not homotopic to alpha.
Well, it's not completely clear.
It is not? Okay, let me. So okay, you want me to prove that if I consider this green path, it's not homotopic to alpha, right?
Well, first of all, homotopic in which class of paths?
Okay.
Do we fix the endpoints?
Okay, so sorry. Okay, yeah, let's do this. Homotopic like this. I mean, fixing the endpoints.
So we fix the endpoints.
Yeah, sure. And this if it goes along the
I agree that these two particular paths are not homotopic, but what exactly is
okay, so yeah, so the space I constructed, I lifted everything on in T, which are homotopic to alpha here. So I'm not touching anything going through this one.
No.
The only
once again, we consider the space of paths. I don't know where, somewhere, which are homotopic to alpha, rel bound.
Yeah, here.
Now, those are paths in which surface? S or
in T.
Okay. So so these paths are these paths are homotopic and they're homotopic to alpha and so what we want to prove is that the lift does not depend, the lift of every such path to T prime does not depend on which homotopy we choose from the path to alpha.
Yes.
And so this may be true, but I don't quite see why.
I mean, the reason I have in my mind, because if you take a path here, and which is homotopic to alpha, so here, I mean, elements of this, I mean, here are paths which are homotopic to alpha, and as they have nothing to do with that handle, so
please make it precise.
Okay.
What does it mean? They have nothing to do with that handle.
Okay. Okay. So let's consider it like this. That let me get back to the picture. I guess I can make it precise this way. Look at the fundamental group of this, right? And take a path here. Take a okay, no, it doesn't concern fundamental group.
So my initial objection was that two homotopic paths can be homotopic in two different ways, for all we know. For example, if we have the two sphere, the north bell, the south bell, any two paths from the north bell to the south bell are homotopic. But the space of homotopies is the sphere one dimension less the circle. This probably doesn't happen here because all surfaces have negative weather characteristics, but this needs to be checked.
I can say this, I mean, to make that thing precise, that, okay, take any path here, anything. So, like, I don't know, something, the thing I said that doesn't concern the handle, I mean, to be precise, it's like this, that, I mean, take something here, maybe it can go here and something, but, I mean, the endpoints are P and Q. And if you consider, I mean, call it P, and if you consider alpha, I mean, just, this is a loop, fundamental loop. My claim is that if it has the generator of the handle, it cannot be homotopic to alpha. So it tells us that when we are lifting paths which are homotopic to alpha, there is no generator of the generator of the one handle doesn't show up. So
again, forget about the one handle of the generator.
Okay, so if we forget about the one handle generator, we have S.
Once again, there are many ways there are many homotopies between two. There could be many homotopies between any two homotopic paths. To choose a lift, you choose a handle.
I should.
And my question was why doesn't the result depend on which homotopy you choose?
Okay, so yeah, I get the question now. Okay, do you agree that on T, by definition, we took a path, which is
basically the answer is because S or T, both of them are spherical, which means the higher homotopy groups vanish. But this needs to be made more precise. Chris, are you still with us?
I'm here.
Okay, so
I'm looking at the text in Hatcher. I'm trying to figure out what's going on.
so my conjecture is the lifts do not depend on which homotopic we choose because all surfaces we have here are spherical. Is it what Hatcher says? Does he say anything?
I don't think he says anything.
But do we really need that? I mean,
Well,
even minutes of
yes,
because we
So he,
well, as I said, for all we know, lift depends on which homotopic we choose. And,
but we have a canonical choice.
by the way, the surface, okay, so the surface we take as T is definitely spherical. Why? Because it has boundary. So the space of homotopics, between any two homotopic paths is basically the space of maps from the two sphere to the surface. Chris and Grisha, does this make sense? So, suppose I have two homotopic paths and I want to show that the space of homotopics between those is contractible. Or at least that any two homotopics are homotopic. This would suffice to prove that the map is well defined.
I'm not sure that what you're saying is correct. I don't think that two homotopics being homotopic means that the space is contractible.
No, it's not the same, but we don't need the space to be contractible. We only need pi 2 to be 0.
Oh, okay. Okay, yeah.
So, suppose I have two paths which are homotopic. And here is a homotopic between them. And suppose I have another homotopic between the same two paths, which is, well, it's hard to draw. Let's say we have another homotopic.
so I don't understand what we're worrying about and why we care. I mean, so Hatcher just claims to construct a subspace.
Well, so the last claim here is this, which we have A prime T alpha.
Yeah. So his claim is that
So basically,
his claim is the following. He says all arcs in this AT alpha space, they're all isotopic to alpha. And so try to lift them to T tilde.
yes.
And so the claim is that there's a unique lift isotopic to a lifted copy of alpha in U.
Well, yes.
Is it this uniqueness that you're worried about, or?
No. It's yes. The uniqueness could be problematic because there could be several isotopics between the same two isotopic paths, and in our case, this is not.
I don't think he cares whether or not there are kind of many different isotopies. He just wants there to be a unique lift that is somehow isotopic to the fixed lifted copy of alpha.
In this case,
it could be isotopic in many ways, and it doesn't matter because he just wants to define a subspace.
well, in this case, there could be several lifts of the same path, and we don't have a projection.
Well, so there's a restriction, right? So he's saying that there is a given lifted copy of alpha that lives in U inside of T tilde.
Yes.
This is given data. And so the claim is that there's a unique lift to T tilde, which is isotopic to this given lift. This is the claim.
Well,
So,
I think
so,
it's,
so
I think it's true. But it's
okay. Let's see. What is T tilde?
Is it the same as T prime?
Yeah, because
Okay, so here is.
I guess I made a mistake here. I mean, it shouldn't be S. It should be T. I mean, let me check that one more time. I guess here it must be T, but if it is T, it doesn't solve anything. Let me check it. But yeah, T tilde is T prime, right?
Okay, so T prime is the same as T tilde.
Yeah, it is T, it's not S.
Okay. So the space of paths inside T is the same as the space of lifts inside T prime or T tilde. Okay. And this is true. Why? Well, because T and all the rest of them are spherical.
Yeah. So, I mean, yes, because it's here. So after that, the inclusion here, let's back and remember what we want. I want to show that this map induces the inclusion here induces rejection here. So let's write this map in the things we have right now. Write this map to the inclusion here. Write it as follows. I mean, it's just the same as that step. First, I go here, just A T alpha, and then by inclusion, sorry, it's not the same. I have this, and I identify this by so it gives me this. If I can do this. What was alpha prime? Alpha prime was here. This is T prime, and alpha prime is just a copy of alpha. So if I consider this inclusion, what do I get? Okay, here. Yeah, I want to show that this map. Again, I want to show that the I is injective. But if I show that this map is injective, this composition, if it is injective, then it shows that I is injective. I mean, injective on pi x. And this is the last page of my notes. But okay, we have to look at the picture here. Look at the picture. I mean, look at the way T prime looks. Okay, what is the boundary of this these red parts? Do you agree that it's just? I mean, okay. I mean, the interior of this red. I mean, each of these red ones is just the upper half plane, right? Because it's the universal cover of some cut surface. Okay. And the boundary is. I mean, so the whole thing is. Upper half plane, but the closure of this, we consider it the x coordinate, x is 0, 2. Is it clear? I mean,
the red part is basically what? It's the upper half plane minus a point of the boundary.
Yes. Yes. No, I mean, yes. I want to say this. I mean, let me just. The interior of this is just
upper half plane. Yes.
Yeah. Or R and or H. What and two?
Yes.
Yeah.
Basically, the picture is literally correct. If we take 1 point here, remove it, and 1 point here, and remove it. Then the red part is literally what it says, what it shows here in the picture, and same for the other one.
And the other thing we need is that is this that let me work with another color. U tilde minus the boundary of T is this. Again, is it clear?
U prime, U tilde. What is U tilde?
This, I mean, the whole red part.
Okay, so U tilde minus delta T. What is delta T?
I mean, just the boundary of T, because I mean, T was the
why is the boundary of T part of U tilde?
No, I mean the part that it has intersection. Maybe not the whole boundary of T. It has intersection, but if it has intersection and if you remove intersection parts.
Okay, so the boundary of T lies downstairs. It's part of T. U tilde is the universal cover of U.
I forgot the reason. I mean, I figured this out, but I don't want to try. Let's see if I can prove something. I just wrote here by hyperbolic geometry. I don't know what it means. Maybe there is something. I guess the point is that we can deform these red parts to U. I mean, I said
I can deform the red parts to U. Okay, yes, this is what I just said.
Yeah,
that's okay. S, the surface in the middle is basically what is shown in this picture plus some handle. So we have handle 1, handle 2, handle or something, but otherwise it's exactly what is shown in this picture. And the red parts are also exactly what is shown in this picture, except we need to remove 2 points from the boundary. And then we get literally what it says here. In particular, it's homotop equivalent to U.
Yeah, I mean, the point is we can deform the red parts
yes,
to U.
The whole thing is homotop equivalent
yes.
to U.
Yeah, okay, so let me, yeah, I mean, so forget about the boundary parts, I mean, it was just, so, I mean, the point is we have a retraction here, R from T prime to U, it's a retraction. So when we have a retraction, so we have here, and it shows that this map is injected.
It's even split injected.
Yes. So it shows that this I is injective. So it can.
Okay.
So it's proved.
Okay, Chris and Grisha, does this make any sense, or doesn't it, or are you too tired to?
I think it's okay now.
So Chris thinks it's okay. Grisha.
Yeah, I think it's fine.
Okay, well, which basically proves it there. Okay, we've run out of time. Are there any questions?
I'm sorry, that's why.
Okay, questions, remarks, criticism, any of this? Okay. Now, what shall we do next time? Let's think. Grisha, you wanted to talk about something, and I've forgotten about.
Yeah, so I thought that maybe I can give a talk about stability of symmetric groups. And if it's too short of a talk, I can also say something about automorphism groups. But I'm not sure if that's okay.
Okay. Гриша, идея в том, чтобы показать аналогию между симметрическими, не просто по обзору Куперса, а показать аналогию между симметрическими группами и группами классов отображений. То есть симметрические группы — это тоже группа классов отображений, только в мерных многообразий. Значит, нам не нужен список результатов в симметрических группах, без всяких доказательств. Нам хочется понять аналогию с тем, что было.
Хорошо. Я могу еще Куперса спросить, в принципе.
Значит, я предлагаю использовать... Да, я, к сожалению, не знаю, что такое обзор Куперса, и сейчас предлагаю... В общем, пришлите его, пожалуйста.
А он вроде был в списке того, что мы обсуждали, в смысле литературы какой-то.
Значит, он был в списке литературы.
Да.
Чего? Серьезно?
Ну, там вот что-то там такой коротенький, там типа лекции 4 про гомологическую стабильность.
Чего? Да, ну, видимо, я уже все забыл. Хорошо, значит, давайте, может быть, с вами отдельно про это поговорим в Zoom. Значит, у меня, то есть, может быть, это теорема Куперса, а не обзор Куперса?
Да нет, это именно такой, ну, на самом деле, даже не обзор, это записки некоторого мини-курса. Давайте.
What Grisha is talking about, it was probably mentioned at some point, but I've probably forgotten question. So there's something in the chat, blah, blah, blah. Cooper's, what is it? It's, okay, so I'm not saying I've remembered, but I'm starting to sort of remember what Chris is talking about. Okay, now Grisha, I would suggest to compare this with what it says in section. In the last section of Hatch's notes, when he talks about symmetric groups as the dimension 0 case of the mapping class groups. So we want to understand this analogy between one and the other.
Right, so I'll try to get you a draft of my notes by the end of the week, and probably we can discuss it over the weekend if you're free.
Okay. And basically, the idea is we have already proved everything we need for to do symmetric groups.
All right.
В общем, идея лишь по максимуму использовать то, что у нас уже было доказано в связи с...
Я понял, да.
Значит, более того, там часть вообще работает произвольной размерности. Вот, а часть для надмерного случая работает все-таки проще, чем для двумерного случая. Okay, well, I think it's a nice application of what we've already seen. So let's discuss this next time. Saman, Chris, do you agree?
Yes. So
Sounds good. Sounds good, yeah.
Okay.
The homology of symmetric groups we want to discuss next.
Yes. Next. Okay, well, then this is probably it. See you next time. I think we've discussed everything we wanted to. If this is not the case, please let me know. And otherwise, this is